Hey, welcome back to Abstract Algebra. In this lecture, we're going to wrap up our work in Chapter 3 on permutations. I want to tell you a little bit about permutations. Have a parity. They come in two flavors, even and odd. So that's the purpose of the lecture, is to tell you about even and odd permutations. I wrote a list of what we're going to try to do in there. I want to define transposition, and then I want to prove a couple of theorems. Instead of writing out the theorems here in the beginning, I'll just go maybe it's easier to you to just refer to them in your book by number. You've got the book. So I'm going to give proofs of Theorem 325 and Theorem 331, and then we'll give some sort of outlines of proofs and just discuss 332 and 333, and then maybe in the class tomorrow, I'm recording this on April 8th. I'll meet with you guys on April 9th. Maybe we can give more detailed proofs of 332 and 333. Okay, so let's get going, trying to keep this thing from getting too long. I want to tell you what a transposition is, and it's an easy thing to do. A transposition is just a cycle that has length 2. Okay, so you remember that the length of a cycle is the number of elements in its non-trivial orbit, and a transposition just has length 2. So a transposition is a permutation in cycle notation that just looks like ij. I goes to j, j goes to I, everything else is fixed. It's called a transposition. Let's look at this example I've got here. I wrote a permutation sigma. It's a permutation in S6. It's a cycle. It's a cycle of length 4. And I have a little claim here that that cycle sigma, I can write it as the product of those 3 transpositions. And if you're looking at sigma, look at those elements 1, 4, 3, and 5. Here's the pattern that I used to write that down. I wrote a transposition that has the first element and the last element. That's my 1, 5. And then the first element and the second to last element. That's the 1, 3. The first element and the next to last element, 1, 4. And I stopped there because this cycle had length 4. Yeah, so you sort of start at the end, always using 1, stepping back towards it. And my claim is that the product of those 3 transpositions, they're not disjoint, they all have the element 1 in them. My claim is that that product will recover sigma. So let's do that just by kind of filling in this array over here. And if we get the same permutation that sigma is, then that establishes our claim. All right, so you got to remember that we feed things in from left to right. So when you're looking at this product of permutations, 1, 4 goes first, then 1, 3, then 1, 5. Any symbol that's not appearing in a cycle is fixed, right? So let's check out what happens to 1. I'm just going to kind of be underlining as I'm looking at the factors that I'm talking about. So this first factor, 1 is sent to 4, which is fixed, So 1 goes to 4, okay? What about 2? 2 is fixed by every single one of those factors. So 2 goes to 2. 2 doesn't occur anywhere. How about 3? 3 is fixed by the first factor. The second factor sends it to 1. The third factor sends 1 to 5. So at the end of the day, 3 gets sent to 5. Maybe you can pause and fill in the rest. What happens to 4? Well, it goes to 1, which goes to 3, which is fixed. So 4 goes to 3. 5 is fixed by the second. Third one sends it to 1, so 5 goes to 1. 6 is fixed everywhere. And if you take a look at that thing, if we write it in its cycle decomposition, we'd write 1 goes to 4, which goes to 3, which goes to, I just lost it, 5, which goes back to 1. 2 and 6 are fixed. Sure enough, that recovered sigma. All right. So I'm going to be kind of, I did this example because it's going to be the kind of heart of our first theorem proof. I'll try to leave the example in view here as long as we can. The theorem I want to prove in your book is 325. It's actually a theorem in section 3.2, not 3.3. And it says that every element in the symmetric group Sn can be written as a product of transpositions. Okay, so you give me a sigma, I can break it down into a product of transpositions. If you like a kind of more colloquial version of this statement, it's saying that every arrangement of n objects can be achieved by interchanging 2 of them at a time. It's kind of an interesting interpretation of that. If you permute n objects, I can achieve that permutation just by switching 2 objects at a time. And in fact, in the proof, I'm going to give you exactly a recipe for how to find those switches. Okay, so let's start trying to prove it. Give me a sigma. I don't want to reinvent the wheel. We've already shown in our work in section 3.2 that you can write sigma as a product of cycles. They're actually disjoint cycles, but the disjoint isn't all that important to me. But right now, that each one of those gamma i's is a cycle. So all I really need to do is convince you that if I can write any cycle as a product of transpositions, then I could write any permutation as a product of transpositions. So that's what I'm going to do. I'm going to show that every cycle in Sn is a product of transpositions. So I'm just going to make a claim like what we did in our example. Here's a cycle. It's a cycle whose elements are called J1, J2, and so on. It has length m. J1 goes to J2, J2 goes to J3, and so on. Jm goes to J1. And I claim that that cycle is equivalent to, look at my pattern again here, it's first thing, last thing, first thing, second to last thing, and so on until you got down to J1, J2. Okay, so that's how I form this pattern. Can you see my dot, dot, dots there? So how am I going to convince you of this? Well, the statement says that two functions are equal. So I basically have to show that they do the same thing to every index in the index set. So if you take some, say, index I that's in our index set, and I is not one of these J's, I isn't J1, it's not J2, it's not Jm, then both sides fix I. They both send I to itself. So we only have to worry about the indices that occur in here, okay? So let's try to think about what happens to, say, J1, for example. All right, so again, we feed these things in from right to left. So you're looking over here, and you see that J1 goes to J2 in that first factor. And then every other factor fixes J2. J2 does not occur again in any of those things. So the rest fix J2. So J1 goes to J2. That's on the right-hand side. That's true on the left-hand side as well. Look, J1 goes to J2. That's what this cycle notation means. All right, let's try to imagine what happens to J2. Okay, well, J2 in this first factor on the right-hand side gets sent to J1. J1 is in the next factor. You can't read it there, but it would be J1, J3. So that thing sends J1 to J3, and then J3 never occurs again. So J2 ends up going to J3. The rest fix it. Okay, it's the same thing as in our cycle. J2 goes to J3. Can you kind of see why this is working? When you hit one of these transpositions that has your index in it, like if we took, say, J3, J3 is fixed by this first factor. The second factor would send it to J1. The next factor sends J1 to J4. So J3 ends up going to J4. So it's going to continue like that until we get to J1. J1 kind of has the most interesting ride. This first factor, or the first factor J1 that sends J1 to J2, and J2, sorry, I misspoke, but this is my third attempt trying to make this video, and although I like you guys, I'm not stopping it and making it again. So I started with J1. I know what happens to J2, J3, and so on. It's Jm, right? Where does Jm occur? It doesn't occur in any of these things until the last one. So Jm gets sent to J1. Okay, so my proof is that both sides of that factored into transposition permutation do the same thing to every index that occurs, so they're the same permutation. Okay, so that's my proof. Let's just illustrate it by example. Can you stop the video and kind of write this thing as a product of its transpositions? It would be, how would it go? You do first element, last element, first element, next to last, and this one would be over right there. And you can just check it one element at a time, that both sides of this thing do the same thing to all those indices. And by the way, if you're wondering, this is an element of S what? That's a good question. N here could be any number that's greater than or equal to 3, and any symbol that's not 1, 2, or 3 is fixed. So they're all fixed by both sides. And let's just check this right-hand side. 1 goes to 2, which is fixed, so 1 goes to 2. 2 goes to 1, which then is sent to 3 by the next factor, so 1 goes to 3. And then what happens to 3? Well, this factor fixes it, and the last factor sends it to 1, so we exactly recover the cycle 1, 2, 3. All right? So every permutation can be written as a product of transpositions, and I've shown you how to do it. You take your permutation, you write it as a product of cycles, you take each one of those cycles, and you apply this recipe to write it as a product of transpositions. Cool. Okay. I wanted to show you in this example, let me erase my messy work here. It's not impossible to write this as a product of some other transpositions. So in other words, this factorization isn't unique. You know, I could stick on 1, 2, 1, 2. So this just means interchange 1 and 2, interchange 1 and 2, interchange 1 and 2, interchange 1 and 3. Well, of course, these first two undo each other. I mean, maybe I should have mentioned this above, but the inverse of a transposition is itself. If you're going to undo the permutation that switched I and j, you should just switch I and j again. So when I multiply by 1, 2, and 1, 2 over there on the end, I'm just multiplying by something in its inverse. That's the identity. It's not going to change it. But it's a different product of transpositions. Those transpositions won't commute, but it's a different product of transpositions. Notice in both cases, the first time I did it, I used 2 transpositions. The next time I did it, I used 4. I could use 6, I could use 8, I could use 10, but I could never do it with an odd number. I could never write this 3 cycle as a product of an odd number of transpositions. That's the next theorem, Theorem 3.31. Theorem 3.31 says that every permutation in the symmetric group Sn can be written as a product of either an even number of transpositions or an odd number of transpositions, but never both. You cannot do it both ways. So I'm going to give you a different proof than what Herstein does. My proof is based on a fact from linear algebra. So let's try to check out my proof here. If you give me a sigma, I'm going to define a certain n by n matrix. Remember, m sub n of r just means m by n matrices, square matrix. I'm calling it A sub sigma. And what I do is I take the n by n identity matrix, the matrix all of whose entries in every row is a 0 except for 1. The 1s are occurring on the main diagonal. Let me make my matrix bracket a little bit bigger there and not put a 0 on the main diagonal. Can you guys tell I'm running out of gas? I'm tired at the end of what has been a long day. But I take the n by n identity matrix, and then I just permute its rows according to the permutation sigma. You know, so for example, if sigma, say, sends 1 to 5, well, then I write the first row of the identity matrix where the 5th row is. And if 5 goes to 3, I write that 5th row where the 3rd row is. So I just permute the rows. I just let sigma tell me how to do it, okay? If sigma is a product of these, say, transpositions, that's the Greek letter tau. I like to use it for transpositions, and I've got m of them. So each one of those taus is a transposition. Then I can get this matrix A sub sigma by swapping 2 rows at a time, m times, right? So I just tau tells me which 2 rows to, tau m tells me which 2 rows to swap, then I swap these, then I swap those. Every one of these things is a transposition. It's just interchanging 2 rows at a time. And when I do all of those transpositions, I will have achieved the permutation sigma. Okay, well, you remember from linear algebra, I should have had you stop the video and try to think about this, but when, well, let me ask you, when you interchange 2 rows of a matrix, what do you do to the determinant? What effect on the determinant is interchanging 2 rows do? It multiplies the determinant by -1. The determinant of IN is 1. The identity matrix has determinant 1. So when this first transition tau m goes, it swaps 2 rows. Well, now the determinant is -1. then tau m minus 1 goes, the determinant is 1 again, and so on and so on. So depending on whether m is an even or an odd number, you've multiplied by minus 1 an even or an odd number of times. The determinant of this matrix, A sub sigma, is going to be minus 1 to the m being the number of transpositions. Okay, well, if you wrote sigma as some other product, the stars just mean that, I have some other transpositions, there's k of them now. Well, the determinant of A sub sigma would have to be negative 1 to the k for the same reason. So these two numbers, m and k, they have to satisfy that negative 1 to the m is negative 1 to the k. So m and k are either both even or they're both odd. If they had different parity, then that equation would say negative 1 is equal to positive 1, and that's not so. All right. So with that theorem, I can make the following definition. I'm going to call a permutation even if you can write it as an even number of transpositions. Otherwise, I'll call it odd. All right. So in our example back up here, sorry about all the scrolling, but this thing, this 3-cycle 1, 2, 3, it's an even permutation because it's a product of 2 transpositions, for example. Yeah, good. So a permutation is either even or odd. Let's denote by A sub n the set of all permutations in Sn that are even. Okay, so I'm going to just focus on the even ones here for a second. And the theorem, the first theorem that I wanted to discuss, I didn't say I was going to prove it, is theorem 3.32, and it says that A sub n is a subgroup of S sub n. In fact, it's a normal subgroup. That the even permutations form a normal subgroup of the set of all permutations. So let's not give a formal proof of it here. It's late in the day, we're tired, we can talk about it in class. Let me give you some ideas for the proof. Maybe some things you can ask me questions about when we're meeting tomorrow. So subgroup test. Okay, why is it non-empty? What's our usual candidate for showing some subset of a group as an empty? We look for the identity in it. So the identity permutation fixes all elements. Okay, well, I personally like to think of that as a product of 0 transpositions. 0 is even. But if you don't like that, here, the identity is a product of, say, this transposition with itself. It's a product of that transposition with itself, so it's even. If you're worried that my work here needs n to be at least 2, that's a good worry. It's true. If n is 1, remember we kind of cast out the symmetric group S1 is a trivial group with 1 element. It's the identity. It's an even, so it's a normal subgroup. It's kind of not interesting. But you're right. If I write this 2 right here, I should say n is at least 2. So A sub n's not empty because it has the identity. What about closure? Closure. You take a couple of permutations, say sigma 1 and sigma 2. They're both even. So what does that mean? It means that when you write sigma 1 as a product of transpositions, you have some even number of them. Let's just write 2k. Sigma 2 is also a product of transpositions, say tau stars. There's an even number of them, let's say 2m. Well, I think I can see that sigma 1 times sigma 2 is a product of how many transpositions? 2k plus 2m. And 2k plus 2m is going to be even. So there's kind of an idea about closure. And I didn't give myself a lot of room here. Actually, let me sort of see if I can give myself some more room here. Just by sliding that up a little bit. Now we have some room for inverse, the third part. So sigma is a product of, say, these transpositions, tau 1 to tau k. Well, Socks and Shoes says that sigma inverse is a product of those things inverses in the reverse order, yeah? But tau is a transposition. it's it's inverse is itself. So when you write these things in the opposite order, they are their own inverses, and there's still an even number of them. All right, so I'm not going to worry about that. Details, we can talk about it in class. I won't fill in my proof box here because it's just a sketch of a proof, but those are basically the ideas. Maybe one of you will take over in the meeting tomorrow and give us a rigorous proof of that. This theorem justifies this name. A sub n is not just a subset, it's a subgroup, and it's got a name. It's called the alternating group. The alternating group. It's a historical term from when people were looking at certain kinds of roots of polynomials. You don't have to worry so much. It's why the A is used, alternating group. You just have to remember it's the set of even permutations, okay? Subgroup. Maybe I'll ask you just a question out loud. This is not in my script, but it's occurring to me. I wonder if the set of odd permutations is a subgroup. Maybe you're wondering the same thing. Okay, last thing we're going to discuss here is Theorem 333. Theorem 333 says that if you're not in that trivial case, if n is at least 2, then exactly half the permutations in Sn are even. Half the permutations are even, half the permutations are odd. That's the idea. So let me give you an idea for the proof of this. We'll talk about it tomorrow. Idea for the proof of this. Let's denote by B sub n the permutations in Sn that are odd. Okay, so what do we know? Every permutation is either even or odd. So Sn is the union of An and Bn. Every permutation is either even or odd. No permutation is both. Sorry, it is empty. Their intersection is empty. Okay, so if I want to show you that A sub n has size n factorial over 2, one way to do that is to show that A sub n and B sub n have the same number of elements. Because if together they add up to everything, no overlap, if they're the same size, then they both have to have size half of S sub n. All right? And one way to show that two sets have the same size is to get a bijection between them. Not a homomorphism, just a one-to-one onto function. So here's how we're going to proceed. For every, say, sigma in An, let f of sigma be the transposition 1, 2 followed by sigma. All right? So sigma is even. It has an even number of transpositions. I've just tacked on one more. Well, an even number plus an even number plus 1 is an odd number. So this is an odd permutation. And then what do we got to do? We need to show it's 1-to-1 and onto. You try that. Tell me about it in the morning. Take that function f, see if you can show it's 1-to-1. What if f of sigma 1 equaled f of sigma 2? You're working in a group. You've got all kinds of theory. Okay, thanks for listening. I hope that this wasn't too much too fast, trying to wrap up this work in chapter 3, but we'll meet tomorrow and talk about it. All right, so I'm going to sign off.